Well, the next one, the next type of cable stayed bridge is what I call a hybrid cable stayed bridge, meaning a steel deck in the main span and a concrete deck in the side span. And the best example for this is the Normandy Bridge in France. A beautiful bridge, and it catch the world record in something 1984, so with 856 meters. There were 4 runners. 404 meters, as you may recall from one of the early lectures, it was Saint-Nazaire Bridge in France, and with 404 meters with 2 towers. On the other hand, we had several bridges with 1 tower only, 300 meter about early Rhine Bridge, then came 320 knee bridge, and in the 70s Flehe Bridge across the Rhine River with something like 340. If we double those spans, we come into the range of 600-700 meters, so it must be possible. After Saint-Nazaire with 404 meters came first of all Skansund in Norway with 530 meters, all concrete, for the overall world record. And after that came in Shanghai the Yangpu Bridge, 602 meters, beginning of the 80s. So things inched up, but it was a jump then to this new world record, 856 something meters. If I have a meter wrong, you can read it all up in the script there, the figures are right. The main characteristics are steel main span, concrete side span. The concrete goes by 116 meters into the main span, which is good for cost. There's a lot of compression around the tower, which the concrete can take easily, and it stiffens the beam, the steel beam, against aerodynamics. So, but 2 examples. 120 meters is a general figure, which rather independent of the main span is good. We come to the possible disadvantage, as always. There's no such thing like a free lunch. I told you, if we gain something, we have to pay for it somehow. Of course, aerodynamics play an important role for this record span. So we have aerodynamically airfoil-shaped cross-section here in the middle, which goes on in the sides. We have rounded towers, and we have 3 types of damping devices for the stay cables. These are about the main characteristics of the bridge. We go into it in some detail. Now, the engineer for all this is my friend Michel Verlogeux. Some of you may remember, don't know whether you're present. Last year, the bridge excursion went to France, and Michel Verlogeux was kind enough to help with Normandy Bridge, and I think Tancarville. He also assisted to get you into the beam. As all the top French engineers, he's a professor at the top university for engineers, the École Nationale des Ponts et Chaussées, where one of your no, you were at another of these grandes écoles, right? We discussed that, but she studied in France somewhere there. An outstanding engineer. I just quote his cable stayed bridges, which is Normandy, Vasco da Gama, in Portugal, and the Millau. Normandy and Millau we will both show in detail. Outstanding engineer. Now, as I said, I was right. 856 meter main span, 116 outside in concrete, and so that remains this part in steel. All this is concrete. Aerodynamically shaped steel girder, closed box of course, orthotropic deck, and stiffened with trough sections at the bottom. Also, this has to go on in the side span because we have to join the two. The side spans have additional webs because they are built by incremental launching, and we need these points as support for the sliding bearings. We start with the tower. They are built on piles in the alluvial soil of the Seine River down to load-bearing strata. A very solid, massive pile cap. And now we come to the tower itself. Again, naturally, for reasons of aerodynamic stability already, an A tower. I hope you recall I explained to you torsional movements of the beam are prevented or reduced when the two tower legs cannot move independently. There's a calculation example even in lecture to prove that. And we have a composite cable anchorage at the top, which means we take the horizontal component in a steel structure, let me call it, and the vertical runs from the steel anchorage into the concrete. So a composite cable anchorage in the tower tip. Construction of the tower, similar as is the usual thing today. Free cantilevering with jumping forms, no sliding forms. Remember, jumping forms I recommend. And we have here then inclined tower legs, which belong to an A tower. Therefore, after we've reached a certain height, we need temporary struts to support them against one another. Free cantilevering goes on. We need a second strut, and then we reach finally the tower head, where the two forms are combined, basically by taking out the inner parts and connecting the two U shells to one cross section, going on with one pair of forms. That of course has all to be prepared very carefully before, but then it works. And here we see what I mentioned to you, the steel anchorage. This is where the cables are anchored. The other side, horizontal component, is taken directly in steel, not post-tensioning, as I showed you for a concrete tower. And here we see how one piece after another is placed on top of one another. Naturally, we have a very precise location of the cable anchorages if we have this solid steel structure. Around is the concrete, because this is all cast into concrete. We need to get the vertical component from the steel tie into the concrete, whereas the horizontal component is taken directly between backspan and side span. We see here how the forms, the outer forms, run on casting the steel core into concrete, making it composite. Here the thing is completed. Looks also very nice, I think. They've, of course, kept up the outer shape, which is somehow rounded, of the towers through the region of the cable anchorage. Now we come to beam construction, which is very good, very consequent, French, rational thing, no question about it. The approach bridges are long because we need a clearance here of something, today about 50, 60 meters, to get overseas ships up through the sand to Paris. And then we do not like to use more than 6% gradient, because from 6% onwards, if the road is frozen, tracks start to slide down again, as one example. So I agree there's not so much ice on the roads in France, but that's one of the reasons why we don't, and nowhere in the world for major bridges do I know that there is a steeper grade of 6%. But that means that we have very long approaches. And when you build the approaches with I just say straight, it's a little bit more complicated, but straight, then you can use incremental launching method. If you come here into the range 45 meters, you don't need auxiliary piers. And so that was done. The concrete approaches are launched incrementally until they come close to the tower. And then we come here and proceed with the concrete beam 116 meters into the main span. However, and now comes the shortcoming which I was mentioning with that no free lunch. It is in the final stage beautiful, economic, stiff, everything perfect. But the shortcoming is we need an additional construction system. We cannot, you see, we have 3 construction systems. We have, or 2 for the concrete. Incremental launching up to the tower. Then we have number 2, free cantilevering in concrete. And of course then we have number 3, free cantilevering in steel. So the cost we pay here is an additional construction system. And that is why most of these hybrid bridges do not take advantage of the gain of having a concrete piece into the main span, because the savings in say, compression material and so on are less than the additional cost for an additional construction system, changing from incremental launching to free cantilever. So that's always an offset. But here it is very consequent, technically perfect. Economically, I'm not too sure. And then after we've completed the concrete beam, cantilevering in, we built the steel beam in free cantilevering. Now let's look at it. Concrete beam shape from the main span plus webs. I've explained it to you. Here we see the piers are done and the beam comes up here launching. Because of the 6%, it's a special type of launching. It's launching, lifting, it's like a staircase. I'm not going into that here. You can read it in incremental launching books, or it's in the script a little bit in. In principle, it's incremental launching. So we do not need auxiliary piers, so we must be in the range of 45 meters. We are 3 meter deep, and we know incremental launching accepts up to 1 in 15 depths to span without auxiliary piers. So 45 meters is the limit in this for a 3 meter deep beam. So that's what it is here. And then we use a steel launching nose for reducing the cantilever moments. Incremental launching is still on its way. You can do that, of course, in parallel. And free cantilevering, the concrete span around the tower, has started. And here we have completed the concrete beam built by two different construction methods. Now, steel beam for the main span. Cross-section, we have already mentioned, it has to be aerodynamically stable, which means airfoil shaped so that the wind does not create big forces of attack. On the one hand, a high resistance, which means mainly high torsional stiffness, which means a closed box with a reasonable depth to width to give us a high torsional stiffness. That's what this beam fulfills. Fabrication in different parts, all by the French steel contractor Eiffel, who is named after the engineer and contractor for the Eiffel Tower, and it was built partly, I think, in the Alsace, partly in Fos-sur-Mer, near Marseille, and then shipped together, of course, from piecewise cross diaphragms to plates and so on. Now, prefabricated, trial assembled in the assembly yard, tried whether the joints are fitting and all that, and then put on a barge and floated in, and again we use a derrick on top of the beam to lift it up. If you remember what I told you on lifting and the beam stresses there, a steel beam with a reasonable height, 3 meters here, is a good candidate that you don't have to do much to the beam during lifting, that the beam can carry it itself. You don't have to tie back and all these difficult things, and that's what worked here. We have one special thing which I will show you later, but in principle it's very simple. The beam can take the construction load itself. We don't need much additional strengthening, much tie back and things like that. Straightforward, beautiful. You see here, by the way, that's the movable housing for welding the sections to one another. We are back in Europe, of course, where we know that we can weld on site. We couldn't build this cross-section in the US. It's not reasonably possible to connect the joints with cover plates and high-strength bolts. Okay, we lift the next piece. We see here the derrick between the cable anchor points. I showed all that to you. Very reasonable here, the welding bridge. And now the new piece is adjusted, temporarily connected with a few bolts, and then welded around. There was one special item here which I think has not been used on any other bridge, and that is that because of the 856 meters, so we have some 425 meter cantilever in steel, we not only have vertical aerodynamic problems to solve, but also horizontally. I mean, just think of a cantilever 425 meters wide. And so what was done, and you can't tie down the thing in the air there's no way. What was done is there was some damping device, I call it very roughly to make it understandable to you, installed transversely, a weight, a heavy weight, running on tracks, and if the beam started to sway horizontally, this load on tracks was initiated to run against these swaying movements and thereby dampening them. It is in some way better explained in more detail in the bridge dynamics section. You can read it up there, but I think you can understand if you have this swaying motion and you have a weight which is supported in such way that it just runs against these motions that can dampen those enough. We have the same in high buildings where we have a weight which can move this way and that way in anti-phase with the structure itself. So it's used for high-rise buildings permanently to prevent them swaying by running against. And this is just applied, this knowledge, for a bridge. But to my knowledge, it's the only bridge where this has been done. It's all very thought through, beautifully designed and executed. I like that bridge very much. Okay, lifting of the last beam element. Now, stay cable system is now the classical parallel strand cable. You know all about it. I've told you that in some detail how to install parallel strand cable, but for good measure we show it here how it's being done. We have the monostrands, you know, 7-strand, 7-wire strand, inside a directly extruded PE pipe, and then it's kept in a steel plate anchorage with wedges and so on. And now here we come to an example. In fact, what I told you that is in the cable lecture, the wind load on cables transferred to the tip of the tower and the beam takes a greater and greater share of all the wind loads or wind moments of the beam. And here we have now reached for the Normandy Bridge that we come somewhere here that the stays actually produce more wind load or bending than the beam itself. And it is here the stay, if we just look at the beam in plan and at the moment here, then the wind on stays transferred to the beam provides 55% of the beam moment here, and the deck and tower itself provides only 45%. So we see here how important it is that we reduce the drag, the wind load, on the stay cables. I've shown you all theory for that, and in this case it was Freycinet, one of the big French cable producers. They used split shell compact stays, which basically means, you can see it here, the stays, the monostrands are installed, and at the very end 2 half PE pipes, I just call it shells, are with a snap-in connection, are pushed together and very, very tightly are on the strand. So there's not a millimeter given away for reducing the wind load. Now the installation, as you will remember, with the strands, they are fabricated in place on the beam from their components, strands and the P-pipes and anchorages. So I've given that to you in all detail not long ago. I just repeat it now. We have here the strands coming by itself on reels, long pieces. Then they are connected to a tie cable, I call it a tie rod, a tie cable, with a so-called shuttle. You remember a shuttle bus going from one to the other back and forth, and that's the same here. Pulling up, coming down, connecting the next one, and so on. So this connector is called a shuttle. Here we see already most of it is in. It's still the next strand comes here from the reel, is of course when it's all in, it's cut. And we see here the strands protruding over the end wedge anchorage. There's a jack chair on which the jack itself sits, and then we have these monostrand jacks, because these parallel strand stay cables we stress by stressing the individual strand, which means small jacks which a person can move, and not the real heavy one for the full cable, which is an advantage. And here I've told you how we achieve that. Although we start with one strand and one after another and only part one strand at a time, stress one strand at a time, how do we end up with all them strands having the same stress, and not only that, but the correct same stress? Well, you can pre-calculate a certain stress, overstressing, but that's temporary, with which you install the first strand. And then, if you stress the second strand, naturally the stress in the first one goes down from here to there. And all you have to do is to ascertain that both strands, after stressing the second one, have the same stress. That's what's shown here. F1 and F2, both of them. Then you install the third one, and again the stress in the first and second goes down. Again you have to ascertain that all the three strands have the same stress, and so on. Then at the very end all the strands have the same stress and the right total cable force. And if there's a little difference, well, in the ultimate state it will creep okay. So it's not life and death that we are 100%, but theoretically that's the way it works. Now, as I said, the Normandy Bridge, 856 meters light steel beam. The one real problem, which will be the problem also in future for increasing spans, is the oscillation of the stay cables. That's the problem. We can build wide, deep steel beams, pre-cantilever them, nothing really new, whether it's 1,000 or 1,500 meters. But the stay cables they are here already, 450, 500 meters long, and the longer they become, they are very sensitive against oscillations. I've given you a whole lecture on stay cable dynamics, if you remember a little bit. Wind, rain, induced vibrations, all sorts of things. And we have different reasons for these oscillations. Very roughly speaking, it's excitation from the wind itself, with wake, say, if we have vortex shedding, but that's all that's small. What brings us to very high amplitudes is from the wind, is this wind rain induced, where we have this little water rivulet in rain forming up and down, which is enough to transform the cross-section out of the circular, and then it's a galloping phenomenon, and galloping goes beyond all limits. That's one. The other one is that if we excite one anchorage point, and we have a sag, like a washing line, you start pulling, you can get that thing swinging a lot. And how to pull? Well, we can have some oscillations of a beam, of a tower, and that, if in the right frequency range, gets big oscillations. I've shown you all the theory in detail in that lecture. And that is the real problem. I say such a bridge is nervous. When I was on the bridge, no heavy wind, nothing. But just standing there and putting the hand of the stay cable, there was not much traffic on it. You could see, what I say, it's nervous. There's always, in this size, you get all sorts of small vibrations, always. It's never quiet. And so you always have a beginning, and once you get another phenomenon, as we said, it starts up. So, quite correctly and consequently, for the Normandy Bridge, 3 types of measures against cable oscillations were taken. First of all, there were helical fillets welded, so to say, onto the PE pipe, which would prevent the formation of these rivulets I told you about wind rain induced. These little rivulets from the water cannot form over long enough distance by these helical layers at the outside. So that's one important measure. The next one, and by the way, here is an example that we have for low wind velocity and rain, as always, in the amplitudes are compared oscillation amplitudes of a stay cable when there is no fillet around the PE pipe, and if there is a fillet. And you see it's very much reduced. It's proven to be helpful. The next measure is that we tie down the stay cables with some ropes or strands, which means that we change basically the eigenfrequency of the cables, because the cable is not, say, supported over 400 meters at the ends, but in between. It's an elastic support, but the eigenfrequency of the cables increases. So it's not so much a damping, but it's a tuning of the cables. And tuning, in this case, to higher frequencies, which is always helpful. The low frequencies, which come with increased lengths, are sensitive. The high frequencies are less sensitive. So that's the second measure. And you see here the people with Abseil technique. It's in the English word. If you use ropes and climb somewhere, a bridge, the English word is Abseil technique. So they use Abseil technique here to climb the cable. Here we see the bridge. It's not really beautiful. I told you about that. Normally the pictures are taken before these are installed because they don't look so nicely, but cannot be helped. And the third, of course, is then some sort of hydraulic damper. I showed you examples, and you can do it rather elegant, like here. But that's the third measure. Can do it at the bottom and at the top anchorage, which is especially helpful against anchorage excitation, things like that, the phenomena I've shown you. So, of course, energy is dissipated there by pressing a hydraulic liquid through very tight holes. It warms up, takes the energy. The other way, which somehow is preferable, is to use friction dampers, where, like in a car, in a friction disc, the energy is dissipated by friction, which creates warmth and so on. Those are the two, hydraulic or friction dampers. Those are the three measures which can help, and which we will all three, I think, need in future, depending a little bit on circumstances. But the Normandy Bridge has shown it as an excellent example. It was all very well considered and structurally done on site. Okay, besides all the technique, it's a beautiful bridge. And as we see it here, and that of course is a favorite with everybody who looks at these bridges. Michel Verloger was kind enough to give that to me in sufficient quality to show the individual stay cable. That's normally the problem, but it's a good picture. So, what have we done in this second lecture today? We've looked into a hybrid cable stayed bridge. Hybrid meaning steel main span, concrete side span. They act as a cant ledge, as a counterweight for the main span, and naturally dead load, if we need it, we provide it much more efficient in concrete than in steel. We saw that something in the range of 120 meters of the concrete span protruding into the main span helps. It's more economic there in the region of high compression. B, it stiffens the main span by giving him, so to say, additional fixity. For the big spans, we need airshaped, airfoil-shaped beam, which reduces the wind load. It should be a box, naturally, in order to have the required torsional stiffness. For that torsional stiffness, we also need A-towers, which help by preventing independent tower movement, which help to increase the torsional stiffness of the beam. And the construction methods shown here for the Normandy Bridge are very typical, and if possible, they should be applied because they are efficient and economic. The long approach bridges with a 50-meter clearance or so, if possible, do an incremental launching without auxiliary piers, meaning span, side span, span length 45 meters for 3-meter depth. If the economic advantage shows that it's worthwhile to use another construction method, meaning free cantilevering for the end of the concrete approach bridges, especially free cantilevering 120 meters into the main span. Do it, but it has to be weighted. It depends on the contractor. The steel beam is fairly standard. It's fabricated in shop, pre-assembled, floated out, lifted up, welded, stay cables are installed, and the next one comes. A new phenomenon comes with the long spans that not only we have vertical oscillations to look at, but also horizontal swaying. And for that, we can install a horizontally moving weight which runs in anti-phase and thereby dampens the movements. So, a very nice, typical, beautiful bridge, strictly designed, very well executed. Remember it, and if you should ever have the luck to be involved in such a bridge, study it first before you do something new. They've thought of most of things. Thank you.